This conference will now be recorded.
Very good evening, students. Today we'll be learning the magnetism in magnetic materials or magnetic materials itself. So where we'll be discussing mainly three types of magnetic materials: diamagnetic materials, paramagnetic materials, and related things. Okay. So before we discuss all these three types of magnetism, today actually we'll be discussing only diamagnetism and paramagnetism. And before we are discussing that, we need to discuss or learn few fundamental terms like magnetizing field, magnetic field intensity, magnetization, magnetic permeability, then magnetic susceptibility, etc. So these terms we'll be learning first, and then we'll just discuss what are called diamagnetic materials or what is diamagnetism, and then what is the origin of diamagnetism, and how do we know a magnetic material is a diamagnet or something else. Okay, similarly we'll learn what is paramagnet and what is uh, the origin of paramagnetism, etc. Okay, all right. So this class is going to be very interesting, and also it will give you some glimpse of origin of magnetism. Okay, so first, let us learn what is magnetizing field. So it is the magnetic field which is applied from outside, okay, which is applied externally to some magnetic material to magnetize it. Actually, if you know one good thing that, so you might know this, if you have a bar magnet, if you have a bar magnet, you just if you bring some pin made of iron, some pins, board pins or something, you just bring here, okay, and you know this is attracted by the bar magnet, suppose now north pole or south pole, whatever it is. Now if you bring another pin, it will be attracted by the previous pin. Okay, see, if you bring some other pin, that will be attracted by the other one, like that. So there, see here, actually there is no direct contact with this magnet. Okay, see, what does this mean? This mean actually, see, this means this particular pin has got magnetized. It has acquired magnetic property upon placing in touch with this bar magnet. Similarly, this particular pin, since this first one is magnetized now, the second pin is also getting magnetized upon keeping in touch with that. So what we are seeing here, we are seeing that a magnetic material, when placed in magnetic field or near a strong magnetic field, then that will be actually magnetized. That means that will acquire magnetic property. Okay, so what we learn here, we learn that when a magnetic material is placed in a magnetic field, when a magnetic material is placed when a magnetic material is placed in a magnetic field, in a magnetic field, A magnetism is induced in that is induced is induced in that. Okay, in that. Okay, so this is actually magnetization. When a magnetic material upon placing in a magnetic field is become magnetized, so that is actually called magnetization. And so we see that we need an external field to apply to magnetize a magnetic material. Okay, see the magnetic field, so magnetizing field, the field which is responsible, the field which is applied from external sources to some object to magnetize it, to some material to magnetize it, that particular field is called magnetizing field. The magnetic field which exists in vacuum or which is applied to any material by an external source, that is called magnetizing field. Suppose I can just give one more example. Suppose, we have already learned solenoid, right? So if the coils are wound in the same direction with same area of cross section with this loop, this is called air core solenoid. Suppose we want to magnetize some magnetic material. If I just take some soft iron or something and then place inside this solenoid, okay, that means the windings of wire is made on the magnetic material and then current is passed through that. So we'll see this will be magnetized, this iron, soft iron core. So this is soft iron core. If nothing is there, then it is called air core solenoid. This is actually soft iron core solenoid, soft iron core, soft iron core solenoid. Now this iron core will be magnetized when a current is passed through the coils, okay, or windings, or each turns. Suppose there are n turns per unit length of the solenoid and each turn carrying current I. Okay, all right. So the magnetic field which is responsible to magnetize it, actually it is mu0 Ni. We know that an air core solenoid produces magnetic field along its axis, and that is given by mu0 Ni. This is in out, like this is outside. So here look, this field is called magnetizing field. Magnetizing field. Magnetizing field. This is called magnetizing field. So the field which is existing in the vacuum, or the field which is externally applied to some object to induce magnetism in it. So this is magnetizing field, and the strength of that magnetizing field, strength means what? The ability to how much extent the applied magnetic field can induce magnetism in a particular material is called magnetic intensity. So what is magnetic intensity? Magnetic intensity is the strength or ability to magnetize other materials, is called magnetic intensity. The strength or ability of the magnetizing field to induce magnetism in other materials is called magnetic intensity. And this magnetic intensity is actually denoted by H, and this is the strength of the magnetizing field. So it is called magnetic field intensity. So this, this could be written as H is equal to N into I. For a solenoid, we know N into I. It is defined, see, its magnetism is defined as the number of ampere turn flow, flowing around unit length of the solenoid. Okay, so magnitude is defined as number of ampere turns, ampere turns, the number of ampere turns flowing per unit length, number of ampere turns per unit length. Okay, ampere turns per unit length, that is N into I. So N into I. Then what is the relation between this B0, which is magnetizing field, and magnetic field intensity? So this is, see, if I just put it here, this H, so we are getting a relationship between B and H as B0 is equal to mu0 into Ni means H, mu0 H. So this is actually relation between magnetizing field and magnetic field intensity. Now this magnetic field intensity H has, then H is actually, H is ampere per meter. So H has, field intensity has unit of magnetic field intensity. So what is that? That is ampere per meter. Ampere per meter. This is the number of turns, no? Number of turns per unit length. Number of ampere turns, okay? Number of ampere turns per unit length. So ampere per meter. So this is a ampere, dimension is this. Okay, ampere per meter. In short, this unit will be, so this is dimension of H. Okay, so these are two terms, so these are two things. See, these are very important to distinguish what is magnetic field intensity, what is magnetizing field. Magnetizing field is just external magnetic field, and it is the strength of the external magnetic field. Now we'll see what is magnetization. See, magnetization is actually sometimes called intensity of magnetization also. Magnetization or intensity of magnetization. Intensity of magnetization. Intensity of magnetization. Okay. This is the this is actually defined as the net magnetic dipole moment. Okay, the net magnetic moment developed per unit volume, developed per unit volume, per unit volume. So if I mathematically write, so magnetic moment, we know magnetic moment is denoted by small m. So magnetization is a vector quantity. This can be written magnetic moment, as you know, this is a magnetic moment, m is a vector quantity. So magnetic moment, net magnetic moment divided by volume. So as I said, if you apply the external magnetic field in a bulk of a material, there magnetic dipoles will be there, and magnetic dipoles will actually orient in a particular direction, and those magnetic dipole moment will actually create a net dipole moment. So net magnetic moment or magnetic dipole moment per unit volume is called magnetization. This is actually the mathematical form. Okay, so this is called simply magnetization also. Now we'll see magnetic induction, which is, see, this is introduction of what is magnetizing field, what is magnetic field intensity, what is magnetization. Now if I place, suppose I'm placing some magnetic bar, some magnetic material, okay, not magnetic bar, magnetic material. So this is magnetic material. So magnetic material, so as you know, magnetic materials, we are just keeping this inside a field. Okay, inside magnetic field we have kept this material field. This is field B, magnetizing field. So what will be the magnetic induction, what will be the magnetic induction inside the material? What is the magnetic induction? What is the magnetic induction inside a material? Okay, magnetic material when it is subjected to external magnetic field. Okay, so that magnetic field, magnetic induction, or yeah, so the magnetic induction which is produced inside a material is actually the resultant of two things. Okay, so the magnetic induction inside a magnetic material when it is subjected to some external magnetic field, applied external magnetic field, then the magnetic induction B, this is actually inside. I'll write inside material is actually the effect of two, or resultant. This is actually the resultant of two things. One is the external magnetic field, external magnetic field, plus the magnetic induction produced by magnetization, that is denoted by Bm. I'll write it. What is this? We know that B0 is the magnetizing field, magnetizing field. What about this? This is the magnetic induction or the magnetic field. This is the magnetic field produced by magnetic field produced inside the material, due to the magnetization of the magnetic material, due to the magnetization due to magnetization. I have already discussed magnetization is m vector. Okay, magnetization, that is net dipole moment per unit volume, that is magnetization. Okay, so what we have learned? We have learned what is called magnetic induction, and that is the magnetic induction means that is the magnetic field inside the material. Okay, magnetic induction means magnetic field inside a magnetic material. Okay, so this is very important to understand. Okay, this is very important to understand that magnetic induction is always inside the magnetic material, not the outside external magnetic field. And sometimes the magnetic induction is also defined as the total number of magnetic field lines crossing per unit area normal to the surface of a material. See, suppose I have a magnetic material whose cross section is like this. So magnetic induction is defined as the number of magnetic field lines passing through it, number of magnetic field lines passing through its cross section perpendicular to its direction. Okay, direction of the magnetic field. So these are field lines. Okay, so total number of magnetic field lines crossing unit area per unit area of the magnetic material. So that is also another way of defining magnetic induction. So but that is very crude definition. We cannot understand what is happening inside the magnetic material. So first of all, if you keep a magnetic material in an external field, so what happens? The magnetic field lines penetrate the material. Okay, penetrate the material and magnetize it. So this is actually denoted, this is mathematically defined like this. So magnetic field inside a magnetic material is actually the sum of the magnetizing field and the magnetic field produced inside the material due to the magnetization. Magnetization means net dipole moment produced per unit volume. And another definition of magnetic induction is that the magnetic field lines, total number of magnetic field lines passing through the cross section per unit area, actually per unit area, but passing through the cross section and also normal to the cross section. So that is important point. Now we will actually see what are the relations. See, I have just now got B inside is equal to, see this B inside, I am just simply writing B. So we have seen this is B0 plus Bm, and this Bm could be written as, so this Bm could be written as mu0 m. Okay, Bm could be written as mu0 m because it is produced by magnetization. Okay, Bm, this is the magnetic field produced by the magnetization inside a material. So it is actually B is equal to Bm is equal to mu0 into m. Okay, let us write this here. Then we get B is equal to so this is B0 plus mu0 m. Again, we have seen that m can be written as chi into h, and B0 could be written as mu0 h. Okay, so this have relationship with h. Therefore, I can write magnetic induction inside a material is B0 sorry, this B0 is equal to mu0 h. We have already written B0 is equal to mu0 h. We can write mu0 h plus mu0 m. Okay, now this m is equal to chi h, I know. So we have okay, so look this, I'll write one more line here. Mu0 h plus mu0 into chi into h. That means mu0 h 1 plus chi. Okay, this 1 plus chi, so this could be written as a quantity called relative permeability. Relative permeability. Okay, it is mu r. It is denoted by mu r mu0 into h. Okay, mu r mu0 into h. See, this term actually, this term as a whole can be written as mu, permeability of the medium. Permeability of the medium. Okay, this is denoted by, so where mu is equal to mu r into, so this is mu r into mu0. This is the permeability of a material. Permeability, now we'll learn what is called permeability. First, let me then finish this relationship. So what we are getting from here, B is equal to mu h. B is equal to mu h. This is magnetic induction inside any material. And mu r, what is mu r we have taken? We'll just write it down and then discuss this a little bit. This is mu r, relative this permeability 1 plus chi. And chi is called susceptibility. I'll define those parameters. So this is things. So mu r is equal to 1 plus chi. Relative, this is called relative permeability. Relative permeability. Okay, relative permeability. So what is relative permeability? What is magnetic susceptibility? We'll define it here. So I'll just keep this in a short. So B, which is inside the material, will be written as mu into H, or mu0 into mu r into H. And this term is called relative permeability, which is 1 plus chi. Okay, and this chi is known as susceptibility, magnetic susceptibility. It is called magnetic susceptibility. Magnetic susceptibility. So, all right. So magnetic susceptibility, we have already discussed this. So what is magnetic permeability and what is magnetic susceptibility? So those two things we have to discuss. So what is magnetic permeability? Magnetic permeability of a material may be defined as the ratio of, see this from here, mu is B by H. Okay, it is the ratio, it is defined as the ratio of magnetic induction to the magnetic intensity. It may be defined as the ratio of magnetic induction to the magnetic intensity. Magnetic field intensity. So this is actually magnetic permeability. It is actually permeability in the sense permeable. How many field lines, or yeah, how many total magnetic field lines can be permeable or permitted. Suppose this is a material, magnetic material. This is placed inside a magnetic field. Suppose this uniform magnetic field is there in this region. So permeability actually determines, or permeability is the quantity which tells you that how many total number of magnetic field lines will pass through this, or how many number of magnetic field lines will be permitted through the magnetic material. That is called actually magnetic permeability. Okay, that is magnetic permeability. Now we'll go to the magnetic susceptibility. What is magnetic susceptibility? Okay, let me just define that here. Magnetic susceptibility. Magnetic susceptibility. What is magnetic susceptibility? Actually, magnetic susceptibility is the measure of the ability of a substance to take up magnetization when it is placed inside the magnetic field. It is actually very similar to the magnetic permeability. That means how much it can take up. See, if you keep a magnetic material inside a inside a magnetic field, actually it actually becomes induced with some magnetization, right? So how much magnetization it can take, a particular material, how much magnetization it can take. that is actually called, it is the measure of magnetization. It is the measure, it is the measure of a substance. It is the measure of a substance take up magnetization. Take up magnetization. Okay, so magnetic susceptibility is denoted by chi. You look this is actually, see, chi is equal to m by h, magnetization divided by magnetic field intensity, chi by h. So this susceptibility is the ratio of two quantities having the same units, ampere per meter. So this also has ampere per meter in it. Okay, this also has ampere per meter unit. This is actually dimensional quantity. Okay, so ampere per meter, this actually is unitless quantity. Okay, this is actually dimensionless quantity. Dimensionless quantity. So magnetic susceptibility, even magnetic permeability also is a, see here, magnetic permeability also is a dimensionless quantity. See, relative permeability. So susceptibility, and see, this was B by H, right? So magnetic susceptibility and magnetic permeability both are actually dimensionless quantity. Okay, so we have learned what is called magnetic susceptibility, what is magnetic permeability, and same relative permeability are actually dimensionless quantity. Okay, and we have learned what is called magnetic induction, magnetization, and magnetism inside a material. Okay, now we'll just try to understand, depending on few parameters like relative permeability, chi, etc., and some external features, the magnetic materials will be classified into three main categories. Okay, three main categories, and we'll learn those categories today. So now we'll see classification of magnetic materials depending on the behavior. See how we classify here. We will classify the materials in different categories depending on the behavior of materials in external magnetic field, magnetic field, materials are classified into three broad categories. Three broad categories, okay? What are those? See, materials are based on the behavior of the magnetic materials in an external applied field. The materials are classified into three categories. One is diamagnet, then paramagnet, and ferromagnet. And their properties are called diamagnetism, diamagnetism, magnetism, then paramagnetism, magnetism, and ferromagnetism. Ferromagnetism. Okay, so these are three broad categories. We'll now discuss what is called, like, how a diamagnet can be recognized and what are the characteristics of diamagnet in an external magnetic field. So first of all, what is the definition of a diamagnet? Diamagnet. So first category we will learn today. Diamagnet. See, diamagnetic substances are those which develop very feeble magnetization in opposite direction of the magnetizing field. I'll write it here. Those which produces, not produce, develop. Better to write develop. Which develop feeble magnetization. and magnetization in the opposite direction to the applied field, in the opposite direction of the magnetizing field. Magnetizing field. So such substances are repelled by magnets. See, what are the properties? Such substances are repelled by magnet. Okay, repelled by magnet, by a magnet. And second thing is actually they tend to move. They tend to move towards tend to move from strong field to weak field region. Okay, to the move. Yeah, move. They tend to move from strong field region to the weak field region. Weak field region. Okay. And we can give some examples. What are examples of this type of materials? See, there are few more properties. Let me just first write those. So rippling means what and all those things. I'll just discuss a bit. See, they have few more properties. What are those? You know, if a magnetic material they expels, see this, so diamagnetic substances, magnetic substance expel the magnetic field lines. I'll tell you what it is. Field lines. That means, you know, if there is a uniform field region like this, and if you just bring a bar magnet and place inside this uniform magnetic field region, then what it will do, you know, suppose this is the bar magnet, it will not allow the magnetic field lines to pass through them. So the magnetic field lines will be expelled. That means they will be repelled. Then they will go like this. Okay. Like this, magnetic field lines will pass. Okay. Magnetic field lines will not pass through them. Okay. They will not pass through them. This is actually expelling field lines. Okay, field lines by diamagnet. All right. So this is expelling of magnetic field lines by diamagnet. See, in case of diamagnetic substance, this permeability is less than mu is less than the permeability. Okay, I'll just write in mathematically. So this means, this means what? The permeability of the material is less than the permeability in free space. Okay, so this is the thing. So permeability mu, which is less than mu 0. Permeability in permeability outside. Okay, see here I can give you some example like bismuth, tin. Okay, tin, it has Sn. Okay, then copper. These are some substances. Silicon, even gold, silicon. These are actually examples of diamagnet. So these are important. Sometimes some material may be given, and you'll be asked to identify which category this is coming into. Okay. So these are actually examples of diamagnetic material. Magnetic material. Okay. See, a perfect diamagnet. Can you give me some example of perfect diamagnet? Actually, a superconductor. Superconductor is a perfect diamagnet. This is important point. You have to remember this. A superconductor is a perfect diamagnet. Is a perfect diamagnet. A superconductor is a perfect diamagnet and with susceptibility -1, relative permeability is 0. Okay, for a superconductor, relative permeability is 0 and susceptibility is -1. That means it exhibits complete expulsion of see it expel, right? So expulsion of field lines. Okay, field lines, complete expulsion of field lines. All right, that means all the magnetic field lines will be expelled. See, in case of normal diamagnet, there may be some magnetic field lines passing through this. But for a perfect diamagnet, all the field lines will be outside. Nothing will pass through them. So this complete expulsion, this is actually called Meissner effect. This actually called Meissner effect. That means no magnetic field lines will be passing through it. This is actually complete. See, field lines are completely expelled by the magnet. Okay, this is actually, say it is mu r is equal to 0. So this is called Meissner effect. Okay, Meissner effect. Just a minute. SSNER, Meissner effect. Okay, now see this Meissner effect actually depending on this maglab levitation. See, magnetic levitation is actually due to this Meissner effect. Magnetic levitation. In Japan there is maglab train. Okay, that means there will be superconducting rails, and also there will be some magnetic uh, superconducting. There will be, see, there will be huge magnetic field anyway this here, and in the train there will be actually superconducting plate. Okay, or I think it is just vice versa. So the bottom of the train will be huge magnetic field, and see the rails are actually made of superconducting material, and when the superconducting materials are actually brought into superconducting condition, then the field lines will be expelled or repelled. So due to that, the huge train will be levitating in air. Okay, levitating in air, and they can move very fast. Okay, those are called maglev trains. Okay, so I'll just briefly discuss the origin of diamagnet today, and then we'll stop. Paramagnet and ferromagnet we'll discuss in the next class. Okay, the origin of diamagnet magnetism. See, in general, there are, see, in a magnetic substance there are huge number of atoms, right? And in atoms there are electrons. So the outermost electrons, or the electrons, are actually orbiting around the nucleus, that you know. Okay, they are orbiting around the nucleus. So this orbiting electron, they will produce magnetic moment that we have already seen. Okay, mu, that is actually called orbital magnetic moment. So this orbiting electron will produce magnetic moment, right? All right, now in case of diamagnetic material, there will be a pair of electrons which are actually producing magnetic dipole moment in the opposite direction. What does that mean? That means the magnetic moments due to different electrons cancel out each other. Occur in pair actually. Okay, they occur in pair with one of them revolving clockwise. See, suppose there are huge number of atoms, as you know, and there will be electrons in each atom. Okay, so suppose some electrons are just orbiting this anti-clockwise direction. Okay, so when they orbit anti-clockwise direction, the anti-clockwise direction, then the current will flow in the clockwise direction. So the magnetic moment will be in the downward direction. So I'll just mark what is what. So some electron, suppose orbiting clockwise, sorry, anti-clockwise, then it will produce the magnetic moment m in the downward direction. Okay. Now some other pair of electron, other electron may move or orbit in the clockwise direction, so the current will flow in the opposite direction. Then the magnetic moment will be in the upward direction now. So if I have a pair of these electrons together, like if these electrons are together or in pair, they cancel each other, they cancel magnetic moment. They cancel magnetic moments of each. Okay. In pair they cancel their magnetic moments. Okay. And thus we will not have any magnetic moment, right? Thus we cannot have magnetic moment. Okay, zero magnetic moment for an atom. But see, when an external field is applied, then the dipole dipole moment produced by the electrons, or the magnetic moment which is actually in the direction of the field, will get reduced, and the other one get increased. Is in a direction of some direction, suppose here, suppose the applied field is in this direction, then the electrons which is producing magnetic moment in the direction of applied field will get slowed down. Okay, slowed down, and this will be speeded up. Thus we'll get lesser magnetic dipole moment along the field direction, and will get greater in the opposite direction. So now if you take the, suppose this is m prime, this is double m prime. Now if you take the net magnetization, now see the net magnetization is this way, h the field intensity, and this will be m direction now. Okay, so there will be a net magnetic dipole moment, in the opposite direction of the applied field. And you know the magnetization is net magnetic dipole moment per unit volume, so that will give you magnetization. So diamagnetic material always develops magnetic moment in the opposite direction of the applied field. So this is how we can explain the origin of diamagnetism. Okay, we'll stop it here for today. We'll continue with paramagnetism and ferromagnetism in the next lecture, okay, or next class. So thank you for your patience. Bye for today.